I'm a PhD student at Lycée, which is in Toulouse in the south of France, and my PhD advisors are Emmanuel Rachelson and Dennis Wilson. And today, I will be presenting our new paper called A Geometric Encoding for Neural Network Evolution. In this paper, we tackle the problem of encoding neural networks into a genome to be optimized with evolutionary methods. We'll be specifically focusing on neural networks with a fixed architecture, in which we'll only optimize weights and biases. There are two main approaches to the encoding of neural networks. The first one is called direct encoding, where each parameter from the network will be encoded as one gene in the genome. The other approach is called indirect encoding, since an intermediate function will reuse the information from the genome multiple times to generate the final network. Indirect encoding reduces the search complexity by using smaller genomes, which reduces the size of the search space. Reusing the information multiple times from the genome also brings up regularities in the final network, and this network will use these regularities to exploit other regularities in the problems. We hence introduce a new encoding, which is GENE for geometric encoding for neuroevolution. Instead of encoding each weight from each connection in the network, we will instead project all our neurons into a Euclidean space of small dimensions, typically 3 to 10 dimensions. And so each of these neurons will have its coordinates in this Euclidean space, which are completely decorrelated from its position in the network. And the genome will be created from the concatenation of all the coordinates of all the neurons in the Euclidean space. To generate and to build the final network, we will generate all the weights for each connections, and for each connection we will compute the distance between the two neurons in the Euclidean space. And so this distance between two neurons will be the value of the weight of the connection between these two neurons in the neural network. So as you can see, GENE heavily relies on the distance function. So the first distance function we studied is the Euclidean distance, because it's the most obvious in the Euclidean space. However, a main problem of the Euclidean distance is that all the value it outputs are positive values. And if a neural network only has positive weights, it cannot evolve inhibition behaviors where one feature will balance the other one. So what we need is a signed distance function. Hence, we introduce the bounded identity function, alpha, which is basically just the identity function bounded to -1 and 1. And we will use this alpha function in the definition of two new distance functions for GENE. The first one is the signed Euclidean distance. It's the Euclidean distance multiplied by the factor that will give it a sign, which is the bounded value between -1 and 1, to avoid it from exploding, of the product of all the components of the vector between the two neurons. And so this product with the bounded to -1 and 1 will allow us to have a signed value, a signed function, a signed distance function. This is hence called PL2 for product and L2, the Euclidean distance. The other distance function we introduce is tag GENE, tag from the protein tag distances in gene regulatory networks. It has two main features. The first one is that it separates the layers, because the first components of the coordinates will be used for incoming connections, and the other components will be used to compute outgoing connections. So changing one value in the genome or one value in the coordinates, we only have an impact on one of these layers instead of two in other distance functions. Its other feature is the exponential decay, which means that two neurons which are close to each other in the Euclidean space will have a strong connection, and two neurons which are far from each other will have a low weight in their connection. We can see this, the impact of these distance functions in the distribution of the weights of an individual that is generated by the evolution with these different encodings. If we look at the individual generated with direct encoding, we can see that it has both positive and negative weights, while the Euclidean distance, L2, doesn't allow it. So the Euclidean distance cannot reach the same individuals as direct encoding could do, while product L2 and tag gene are both able to cover the same range of values as direct encoding, although the distribution of these weights is a bit different. To evaluate these encodings, we will train fully connected neural networks on a set of reinforcement learning problems. A suitable task for this is the arcade learning environment for the Atari games. This environment provides a memory description of each game state in the form of a vector of 120 values. So we will optimize neural networks to output the best action to take given a state. For the optimization of these neural networks, we will use two evolutionary strategies and compare them. The first one is SNES for separable natural evolutionary strategy. It was specifically designed for problems of high dimensionality, for example, NeuroEvolution with direct encoding. And so its complexity is linear with the number of genes in the genome. The other evolutionary strategy is XNES for exponential natural evolutionary strategy. It is similar to CMAS in a way that it relies on matrices operations where the matrices are size n by n, with n the size of the genome. So its complexity is quadratic with the number of genes, which makes it impossible to use with direct encoding because of the size of the network and the number of genes in the genome. Then the algorithm cannot run with these many parameters. So we tested so if you look at the results of these encodings, both gene and direct encoding, with SNES and XNES, we can see that on many games, gene can find similar results to direct encoding, which means that the encoding and the reduction of the dimensions does not block the optimization algorithm from finding the good individuals and from exploring the environment in the final space, which is the neural network space, in the behavior space. And although on many games the results are purely similar statistically, we can also see that on a few problems, for example, ice hockey on Atari, using gene outperforms using direct encoding, possibly because reusing the information from the genome multiple times allows to bring up regularities in the network, which then exploits these regularities in the problem, which the direct encoding does not do. On other problems, such as sequest, we can see that gene does not outperform direct encoding using SNES. However, using gene allows us to reduce the size of the genome such that we can then use XNES with gene, while we can't use XNES with direct encoding computationally. And on sequest, for example, using XNES allows us to have better results than using SNES because of the way it optimizes. So here we can see that the two advantages of indirect encoding, which are reducing the size of the network and bringing in regularities, both sometimes allow us to outperform direct encoding. But although on most games, the results from direct encoding and gene are similar, at least in terms of scores, we can see the gene still reduces the size of the genome a lot, from 5,600 genes with direct encoding, which is the number of connections in the network, to 800 genes with gene in 3 dimensions, which is what was used for the results previously. And it doesn't have a huge impact on SNES, since SNES was specifically designed to handle problems with high dimensions, such as NeuroEvolution with direct encoding. However, if we look at the optimization with XNES, which sometimes yields better results than optimizing with SNES, we can see that for one update, so for one step of creating a new distribution before sampling the population in the evolutionary strategy, we can see that the time to do this step is divided by 80 by using gene, and the memory consumption is divided by 60 between using direct encoding with XNES and gene. So this paper is the first introduction of the gene framework, and there are many ways to go and many leads to follow if we want to improve it. The first one is, of course, the question of distance functions. Since we have designed a few distance functions and tried them, but there are many new functions to create, and also the distance functions could be used, it could be optimized with the genomes through coevolution. Gene is also able to be used, can be used with backpropagation if the distance function is differentiable. So gene could be optimized with gradient descent instead of evolution. A third option is to explore hybrid encoding, which is the switch between direct encoding and indirect encoding, so gene, between direct and gene, during the evolution. So when one of them reaches a plateau in performance, then we can switch to the other one to exploit its benefits. And another thing that we need to be able to compare gene to other algorithms and encodings is also the encoding of convolutional layers and recurrent neural networks to be able to compare it, for example, on tasks such as the arcade learning environment, but using the images instead of the memory. Finally, also one goal of the future development of genes is to be able to compare the performance of gene with the one of other encodings, such as hypernit or discrete cosine transform. And this is both in scores that can be attained, but also in memory compression and in time improvements due to the reduction of the network of the genome size. So if you want more details and more results on the gene framework, the paper will be available in the proceedings of the 2021 GECCO conference, and the code will be available online on GitHub.